Hey guys, welcome back. Day 33. We're talking about solutions today. All right. And so a solution, we talk about a solution. We'll zoom in here. Solution. There are two parts of the solution. There is the solvent and the solute. All right, so what are they? All right, so if we look at the solvent, solvent is the major component. The major component, all right? It is what the solute is dissolved in. All right, it's what the solute is dissolved in, right? So most of the time, water is a solvent, which is an aqueous mixture, right? But solutions can be in any state, right? So a gas solution can happen. Air is a perfect example of a gas solution. So if you have air, nitrogen is the major component, right? Okay, nitrogen is the major component, and that would be the solvent. Oxygen is the second component, which is the major solute. Then argon would be the third component, right? And so that is 99.9% of air right there, right? And then everything else is trace gases. So air would be a solution of gases where nitrogen's the solvent, so to speak. All right, you would have liquid ones, right? We have a lot water can be, but there's also non-water, right? If you use like turpentine or paint thinner or organic solvents at home, those would be solutions as well, right? With an organic solvent, gasoline can be a solvent, all right? If you needed it to be, all right? Some people use it as a solvent to clean spark plugs and whatnot, and then there's solid ones, right? Old dental fillings were solutions. Okay, so they can still have a solid solution, right? And so when we talk about a solution, right, solutions are homogeneous. Right? Homogeneous mixtures. Right? It's a mixture at the particle level. All right. Of course, aqueous solution is when water is a solvent. Let's talk about the solute. So most of the time in Chem 1, Chem 2, water is going to be our solvent, and that's what we're going to use, okay? You take organic chemistry, water is not the solvent, and that's okay. It can be, but it usually isn't, more often than not. Right now, in Chem 1, Chem 2, we are going to have water as a solute, all right? And that's the minor component, all right? This is the minor component. What is dissolved? Now, when we talk about solutes, if I were to have a beaker here, okay, and it had some type of liquid in there, all right, perfect. And then we had 2 electrodes in there. We had a battery, all right, terminal wire connected there, and this would go in. And then there's like some type of resistor, right? Some type of resistor. And click down there, right? The question is, there's some options. The light bulb can be off, right? It can be off. So one option is off. The second option, the light bulb could be dim. So it could be dim. Or the third option It can be bright. Beyond bright. Okay? Those are your three options, right? It could be, right? It can conduct not at all, right? It can conduct poorly, or it can conduct well. Those are your three options. So, if it does not conduct, we call those non-electrolytes. Non-electrolytes, all right? If it does conduct, we call them electrolytes. All right? What's the difference? Non-electrolytes have no ions in solution. Okay? All right? So they do not conduct electrons. All right. So what does that mean? Molecules, solids, gases, liquids. Those are all non-conductors. So like sugar, carbon dioxide, right? These alcohols, these are your proteins. These do not conduct electricity. They're non-electrolytes. Electrolytes are the opposite. They conduct electricity. And then you have ions formed. Okay. All right. And so then there's two types. Strong and weak. All right. And so if we zoom back out here, we got our strong electrolytes, light bulb bright, and our weak electrolytes, light bulb dim. All right. Okay, that's the difference between the two of them. Strong and weak. All right. So weak electrolytes, not many ions formed. What does that mean? So if I take something like, oh, that's a highlighter, sorry. HCN is a weak electrolyte in water. If this reacts with water, all right, H3O plus CN minus. Weak, this is around, it's usually less than 10% go over, right? Sometimes a little bit more, but roughly less than 10%. Very little go over. Few, right? We'll put few down. Strong electrolytes, right? Hydrochloric acid is one of your strong electrolytes. We'll cover that in a second. Plus water. Go into hydronium. Plus chloride. If we do that, we got about 100%, right? Almost all. Almost all go, all right? And so what we need to do is to recognize the difference between strong electrolytes and weak electrolytes. How do I tell the difference? Glad you asked. Here we go. So first, we're going to start with acids. Again, acids are something that usually have, in Chem 1, acids usually have H out in front, right? And then usually it's HX, right? Like HCN would be HX, or H, I don't want to use blue, let's use purple, YO, right? With a polyatomic ion, all right? And so if you look, here's HX, 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 here's HYO, HYO. And I have a mistake here, I just noticed. This should be NO3. Let me white that out, put a 3 there. Make sure you have NO3. There is no NO4. All right, so those are your strong acids. There are in my class, there are 7 strong acids. All right. Okay. Now, are there more than 7 strong acids? Yes. Okay. Yes, there are more than 7 strong acids. I only expect you to know 7. I don't think that's enough, and that's going to help us in Chem 1 and Chem 2, right? To know these 7 strong acids. Unless otherwise told, every other acid is a weak acid, right? So like HCN, HF, H2CO3, HC2H3O2, H3PO4, and the list goes on and on and on and on. All right, those are all weak. Now, what's the difference between a strong and a weak acid? All right, when I was in your shoes, I didn't grasp this. All right, I thought strong acids were dangerous, weak acids were not. That's not true. Okay, strong acids. All right, what that means is when the strong acid hits the water, the H and the Cl separate, right? Like our example up here, right? This separates into hydronium and chloride, right? Because H plus is the same thing as H3O plus, the same thing, okay? So that's fat, right? And so if you think about a reaction, which is bond breaking and bond making, right? Well, if the reaction to happen, if half of it's done, right? The bond's already broken, right? Then it typically reacts faster than when you get to break and make a bond, right? So HCl, bond's already broken. So you don't have to worry about breaking the bond in the reaction. You just make the new one, right? So it typically react faster, right? That doesn't necessarily mean they're, right, any less or more dangerous. They just happen to react a little faster. Okay, you answer all these, right? You can get this guy right here, glacial acetic acid, which is almost pure acetic acid. That's dangerous stuff. You don't want to play with that, right? This has a LD50. That's probably on the screen the most deadly. This has killed many people. I think it was used in the Holocaust a lot of times, right? Is the gas coming out, all right? Very dangerous. This one is dangerous, but this one is stomach acid, strong acid, 0.1 molar HCl, all right? And so you wouldn't want this one or this one in your stomach, okay? But that's fine to have in your stomach. So it just depends on the acid, the amounts, all that stuff. So strong and weak, all acids can be dangerous, right? Strong acids dissociate completely, are strong electrolytes. That's the difference. All right, moving on. Bases. Bases, as you see, right? OH for a base. So strong bases. All right, the strong bases, they have complete ionization. So what does that mean? That means if I have, I don't know, NaOH, right? Solid. It's not black, is it? That's black. Right, it means it 100% goes to Na plus OH minus. Right? So what are they? So it's lithium hydroxide, sodium hydroxide, potassium hydroxide, we got rubidium hydroxide and cesium hydroxide. We also have BeOH2, and then we have, we go just down, Mg, Ca, Sr and Ba. Right, with all these hydroxides. So those are strong bases. Another one I want to talk to you about, CaO, calcium oxide, which is lime, is probably one of the most important strong bases, because when this separates, you get Ca2 plus O2 minus, and then the O2 minus reacts with H2O here to give you 2OH minus. So that's what that does. So it's very similar to calcium hydroxide in that sense. Now, our most common strong bases are these two. We use this one and this one in lab. Obviously, lime is probably one of the most common bases in the world because it's used to raise soil pH and other things, and that's very important. But in the lab, we like sodium and potassium hydroxide. They're relatively soluble, all right, and they work. We do not use rubidium hydroxide or cesium hydroxide because they're too dangerous. They dissolve the beaker, all right? Technically speaking, beryllium hydroxide is not a base. And then on the second period, right, group 2, second group 2, magnesium, calcium, strontium, and barium, they react like a strong base, but they don't dissolve well. But those are the strong bases. So for our purposes, group 1 and group 2 metals, hydroxides, are our strong bases. Weak bases, ammonia and its derivatives. So anytime you have N, it has a lone pair, and 3 bonds. Doesn't matter what it is, that is a base. That is, so it doesn't matter what these elements are here. Doesn't matter what that atom is, that atom or that atom. Those, whatever they are, it doesn't matter. That's a base. Salts. Salts is the last one. Anything ionic and aqueous. All right. Obviously, if it's a solid, then it's not going to be as strong. Okay. So we need to recognize those are the strong. So everything is going to be either a non-electrolyte, an electrolyte that dissolves in water, and we need to know if it breaks apart fully or not. That's all we need to know. And so you got your strong acids, your strong bases, and then your salts. Those are the only strong electrolytes. Anything else, the molecules, everything else, not. All right. So when we talk about these aqueous reactions, there's 3 equations that we get to talk about. All right. There's the molecular equation, which is the balanced chemical reaction. This is the balanced chemical reaction. That's all that is. That's what we've been doing. The complete ionic is different. All right. That means the chemical equation showing all the species, so how they actually exist, right? HCl doesn't exist as HCl, right? The strong acid, hydrochloric acid. It breaks apart in solution. And so we want to know that, right? So when we do this complete ionic equation, we want to know all the things as they actually are in the water, all right? And then finally, the net ionic is when we have a chemical reaction, we want to show you only the species or only things that actually change, right? And everything that doesn't change is called a spectator ion, and we'll cover that. So when we write these complete ionic equations and we write these net ionic equations, we always use anything that's not a strong ion, right, a strong electrolyte, we put them together, right? That's in the non-ionized or molecular form. So if it's a solid, precipitates a solid, right? A gas. We also have liquids. Weak electrolytes, since more like 9 out of 10 are together, we just consider them together. That makes sense, right? Because most of them are, right? Like if you had a 90% chance of winning the lotto tonight, you'd probably go play the lotto tonight, right? Because you just have to do it. In 10 days, you're going to win 9 times. I mean, it's a pretty good chance, right? You would do that, right? That's not the actual odds, but that would be the, like, yep, 9 out of 10 chance, I'm going to go for it, all right? All right. Now, when we talk about, right, when we, the next topic we're going to talk about is precipitation. So we talked about the electrolytes. And if you remember now, we're moving on to types of reactions. This is one of the, like a double replacement reaction or double displacement reaction where we have an insoluble solid product. All right. Now, solubility rules. You do not have to memorize these, but it's kind of good to know them. And so know the general. These are the general ones. All right. This is not an exhaustive list, but generally speaking, right? lithium, group 1 metals and ammonium are always soluble. That's just what it is. So if you see lithium, sodium, potassium, rubidium, cesium, we're not going to do much with rubidium, cesium. You're not going to see that much except in chemistry land here. Ammonium is also very soluble. All right. The other anions, nitrate, acetate, and chlorate, they're soluble. All right. And so when you see those, we use a lot of those salts. All right. A lot of nitrates are too. We just don't use nitrate much. But that's why they put these things in certain foods to, because they're soluble in water. Now, chloride, bromide, and iodide are soluble, but there's some exceptions. All right. So if I see chloride, it's pretty much going to be have an AQ after it, except if it's paired with mercury, a 1, silver, or lead 2. And then sulfate soluble except with those. Now, these are the no-goes. These are not soluble, all right? Except when you pair them with group 1, basically. That makes sense? All right? So, hopefully you use this chart to figure out what's going on, right? But again, I would recommend knowing that group 1 and ammonium are soluble and nitrate, right? Acetate, nitrate, right? So those top 2 green lines, I would recommend kind of knowing that. It just makes things faster, right? Especially if you plan on taking Chem 2 and then further. It's good to know those. All right, so here's an example. We have a molecular equation, and because we don't have any coefficients, go ahead and check to see if it's balanced. And if you look in, you'll see it's balanced, right? 1 silver, 1 nitrate, 1 sodium, 1 chloride, 1 chloride. We're balanced. And there's your solid right there. All right. So that's your molecular equation. It's balanced. Good. How do we do the complete or detailed ionic equation? Well, I have to recognize what is AgNO3. What type of compound is it? Well, that looks like it's a salt, right? It's ionic. And AQ, right? And aqueous. So that means my complete ionic, I'm going to have Ag plus AQ plus NO3 minus AQ. Now I got to look at NaCl. NaCl, that would be ionic, and AQ, aqueous. So that means I'd get Na plus Cl minus. So when I look at this, if I had a beaker here, again, if I had a beaker, and in this beaker was my liquid, all right? And if I poured these 2 solutions in, what would happen? They separate, right? Silver and nitrate hit the water, they're in the water and separate, okay? Sodium chloride hit the water and they separate. Now, obviously, there's a maximum, right? We can't put in, 100 kilograms of sodium chloride into a glass of water. We get that, all right? But within reason, they're going to separate. They're soluble within their solubility limit. And so, right, that's what happens. These ionic compounds hit the water and they separate, all right? Well, on the other side of the arrow, right, silver chloride. Silver chloride is ionic and solid. All right? So since it's solid, it stays together as AgCl solid. Sodium nitrate, ionic and aqueous. So that means you get Na plus AQ and NO3 minus. So now, what changes here? The actual chemical change is we have a solid product, right? So if we do that, chloride is involved and silver is involved. That means nitrate and sodium right here don't do anything. You see that? So these are all what we're going to call spectator ions. They're there. It's very important they're there, right? Because I can't just have silver ion in solution. You can't just, hey, do you have a bucket of silver ion? No, we don't have just silver ion. We don't have just nitrate ion, right? We have to have like silver nitrate. You got to have a cation and an anion. Everything's neutral, right? And so when you mix these, right, the sodium and the nitrate don't do anything. We actually don't make sodium nitrate. They're still floating around in the solution. The silver chloride precipitates out, all right? So the net ionic would just be Ag plus Cl minus going to AgCl solid. And that's our net ionic equation, right? It's very important to know that sodium and nitrate are in the solution, but if we were doing chemical equations with stoichiometry and doing numbers and such, these are the amounts that we care about, all right? So that is precipitation. The next type of reaction is gas formation, right? And that is where you make a gas. That's just it, right? We just make a gas. So the molecular equation here, and it's balanced because I got a 2 there. I got nickel 2 carbonate with hydrochloric acid going to nickel 2 chloride, water, and carbon dioxide gas. All right, so now we need to figure out what these are in the complete ionic, right, reaction. And so nickel 2 carbonate would be ionic compound, metal and polyatomic ion. So it's ionic and it's solid, so it stays together. So I'd have NiCO3 solid. HCl. Well, HCl is an acid. It's one of my 7 strong acids, so it's a strong acid. Strong electrolyte, which means I get 2H plus 2Cl minus. And it's important to have both of them there. That makes sense? All right, I got to have both of them there. So that 2 is distributed because in our overall reaction, we need to have the right number of ions. Nickel 2 chloride, that's ionic and aqueous. So therefore I get nickel 2 plus 2 Cl minuses. Water. Water is a liquid. So water stays together. It's a molecule. CO2 is a gas. Molecule stays together. All right. Do we have any spectator ions? Well, if I look, see how Cl here and Cl here are spectators? We'll just color that in. I don't like that. Yeah. I don't know if I'll be able to erase that. Sorry, we're going to have to do it this way. There we go. That's better looking. All right, so my net ionic equation then would be NiCO3, nickel 2 carbonate, plus 2H plus. So this is why, if you've ever heard, hey, you just got to add acid. Well, it doesn't really matter what strong acid. You just need to add a strong acid. Because as long as it's a strong acid and the next side is soluble, right? Nickel 2 chloride would be soluble. It works. So it doesn't work with every strong acid, but some of them, right? But that's acid. When we say acid, H plus, you get nickel 2 plus H2O plus CO2. So that's what we have. All right, so now we have the day 33 examples. My recommendation, pause me now, right, and try these, and then see how we do. All right, that's my recommendation. All right, hopefully you paused me, tried them, and let's see what we got. All right, so for our complete or detailed, silver nitrate, Silver nitrate is ionic, so I get 2Ag plus 2NO3 minus. Oh, that's a horrible Q. Did it again. All right. Sodium chromate, ionic and aqueous, 2Na plus CrO4 2 minus. Other side, sodium nitrate, ionic and aqueous, 2Na plus 2NO3 minus. Don't have space. I'm going to try to fit that in there. Silver chromate is a solid, Ag2CrO4 solid. All right, there's my detailed with everything there. The net, well, what's involved? I would recommend, I like doing it this way. So when I was taught this, it was, hey, identify your spectators. I like identifying what's involved. Silver and chromate. All right. Then sodium and nitrate are my spectators. All right. Now, typically your spectators are going to be this compound, right? Typically that's going to be this compound, but not always. But in these double replacement reactions, it is. All right. So now our net ionic equation would be 2 silver ions plus chromate going to silver chromate. That's it. Now, there's a lot of detail with this, if you notice. There's a lot of superscripts and subscripts and state symbols and coefficients, and all of them are important. And so if you're doing homework, especially homework on the online platform, and you're getting frustrated, just deep breath. Make sure we have a coefficient if we have it, a charge, a state symbol. All right, just that's typically what's going to happen. Sometimes you might have to like walk away, walk around the house, do something, come back, and then get a fresh eye, like freshen up your eyes a little bit for it. All right, because there's a lot there, and as we're learning this can be frustrating to do, but it's important to just keep practicing and do it. All right, keep that attitude positive, and you can do it. All right, B. Let's see what we got for B. Our complete. Sodium sulfate, ionic and aqueous, 2Na plus, right? Plus SO4 2 minus. Lead 2 nitrate. And again, if we're having issues with separating these, I would review the naming and formulas, all right? I would review the naming and formulas so that we get this. Again, that's a good skill to have. And if this is the only chem class, it's tough. I apologize, but it's an important skill. So we got Pb2 plus 2NO3 minus. And then we get lead 2 sulfate, which is a solid, 2Na plus 2NO3 minus. So if I put that right in, I would be wrong because I did not have AQ here and AQ there. All right, make sure we have all those state symbols. I know it's tedious, but that's just how it is. Net. Well, what's our net? I have sulfate plus lead. Going to lead 2 sulfate. Now, that's great. Most of the time, you'll see the answer key written Pb2 plus, right? Cation, they'll just switch it on you. All right, because as we learn this, it's always cation, anion. Cation, anion. So a lot of times people just switch it without even thinking about it because we do it so much. And that's okay. If you put sulfate first, it should be fine. All right? It'll be fine for me. But that's just so you know that the answer key will probably be in orange instead of the red. All right. HCl, NaOH, HCl, what's that? So in our complete here, hopefully you recognize it's a strong acid, right? And we have a strong base. We have a salt, and of course water. So our strong acid, H plus, AQ plus Cl minus. Strong base, or ionic and aqueous, however you want to do it, Na plus AQ plus OH minus AQ. Sodium chloride, salt, soluble in water. And all right, our net. What's our net? Looks like our net is just making water. H plus, OH minus. So the strong acid, strong base basically just makes water. Kind of nice, huh? For D, what do we have here? Well, for our complete, H in front, that's an acid, but it's not one of my 7 strong. So this is a weak acid, which means we stay together. HC2, H3, O2, AQ, right? It's a weak acid, so we keep it together. Now, strong base here still. So we get Na plus OH minus. Sodium acetate. That's ionic and aqueous, right? And so I get Na plus AQ plus C2H3O2 AQ. And then water is a liquid. So now I only have one spectator ion, and that's the sodium. So for my net, I get HC2H3O2 in solution here, plus hydroxide. Go into acetate. And water. All right. So that is what we have there. All right. So that's a weak acid, strong base, or strong base, weak acid. All right. Again, hopefully you did these. All right. If you didn't, I would recommend pausing me and doing them. Hopefully you paused me, we did them, and we're going to keep going here. All right. So I'm going to go kind of fast. Again, if you need to reach out to me, feel free. So for our complete or detailed, I get 2K. Well, is it balanced? Oh, I don't know if these are balanced. Oh, it's not balanced. Right? 2K, I need a 2 there. 1 sulfate, 1 sulfate. Yep, now we're balanced. Okay, so 2K plus AQ plus sulfate. All right, because what type of reaction is this? Hopefully we recognize this is a double replacement or double displacement reaction. All right, and my net would just be what I'm making calcium sulfate, right? So it'd have SO4 2 minus plus calcium going to calcium sulfate. Next one. This is actually an acid-base reaction, but it's a weak acid, right? We don't know that yet. And so that's okay. But ammonium chloride, that's also ionic, isn't it? So in my complete, I have NH4 plus AQ plus Cl minus. Strong base, Na plus OH minus. We got water, which is a liquid. We got ammonia, which is a gas, plus sodium, plus chloride. And so that gives me a net of, I got ammonium on both sides. I have hydroxide on both sides. Go into water on both sides. Well, not on both sides. I'm sorry, I'm saying I have ammonium on both sides. I don't have it on both sides. That's the point. I don't have them on both sides. Hydroxide, I don't have on both sides. Water, I don't have on both sides. Ammonia, we don't have on both sides. And that's it. So the spectators, right, were chloride and sodium. Right, and so the actual reactions, ammonium, right, hydroxide, water, and ammonia. All right. C are complete. We have, again, this is a double replacement reaction. So I'd have, now I have a question for you, if you're listening to this still. If this, instead of having this S right here be an S, if that was AQ, what would happen? You would write no reaction, if that makes sense. So if calcium phosphate was actually soluble in water and had an aqueous next to it, you would say no reaction, right? Because all the ions would just be floating around. I don't think I said that yet in this video, so that's why I want to point that out. But because it's a solid, it's reaction. And so we got calcium. Oh, is it balanced? 2 nitrate. Ah, no, it's not. I need to put a 2 here. Well, no, let's look calcium phosphate. Calcium's a 3. And phosphates is a 2. So that means I need a 6 here. There we go. Now we're balanced. Whew. So we have 3Ca2 plus 6NO3 minus. Holy moly. And then we have 6Na plus. Oh, come on. Plus 2PO4 3 minus. Giving us Ca3PO4 2 solid. 6 sodiums. 6 nitrates. There we go. And our net ionic equation would be what? 3 calcium ions plus 2 phosphates, giving us calcium phosphate. All right. Complete. Oh, balance. Balance. No. So I have 2 potassiums here. I need to put a 2 here, it looks like. Then I need to put a 2 here, and I think we're fine. Because now we have 2 acetates, 2 potassiums, 2 potassiums, 2, and 1. Yes, that's good. All right. So our complete, I have acetic acid is a weak acid, so 2HC2H3O2. Strong, 2K plus, TO3 2 minus. Water, of course, is water. Carbon dioxide, of course, is carbon dioxide. And potassium acetate is strong. All right. So it looks like potassium is my only spectator ion. So in the net, we have 2 acetic acids, plus carbonate, go into water, plus carbon dioxide gas, plus 2 acetates. All right, so we're going to do a lot of these, all right, throughout Chem 1 and Chem 2 even. And so just more practice. If you have any questions, reach out to me, because I think that's it for this. Yep, because next up is acid and base. So that ends today. Let me know if you have any questions, and we'll see you next time, guys. Take care. Bye.